Not that complicated. With Ava and Jacob.
Hi there, welcome to Pulley Systems with Jacob. Let's get started with a simple two-mass pulley system problem. A block of mass 8 kilograms sits on a rough incline that makes an angle of 30 degrees with the horizontal. This block is connected by a light, frictionless string over a pulley to a second block with mass 12 kilograms, which hangs vertically. The coefficient of kinetic friction between the rock M1 and the inclined surface is 0.25. Now we take gravity to be 9.8 meters per second squared. It's time to find the acceleration of the system. It always helps to draw out the problem right as soon as you're reading it. In the problem, it states that mass 1 is on the incline and mass 2 is hanging vertically downwards. It always helps to label which mass is which and also the theta in the bottom left corner. Now onto the most important step, your free body diagram. You cannot get a proper solution without a correct free body diagram. Okay, so starting off with the forces on M2, we have the force of tension going upwards, and we have the force of gravity going downwards. Okay, moving on to M1, we have the normal force, which always acts perpendicular to the surface, and then we have the force of gravity, which always acts downwards towards the ground. Then we have the force of tension, which always acts towards the center of the string. Then we have the force of friction, which always acts opposing to the motion. Our next step is to set up our system of equations. First, I like to write out our given, then our required. Let's start off with the first equation of mass 2. It's important to choose the direction of the system, and in this case mass 2 is heavier than mass 1, so I know the system is going downwards. After choosing downwards as positive, I know that M2G is going downwards, so that means that it's positive, and I know that the force of tension going upwards is going against the motion and is negative. According to Newton's second law, all the forces acting on the particle need to equal the mass of the particle times the acceleration of the particle. Putting that all together, you get M2G minus Ft equals M2A. Now let's move on to the second equation for mass 1. Moving on to mass 2, we know that there's 4 forces acting on this object. We know that the force of tension is going upwards, and we know that the force of friction always opposes the motion, which means it's going to be negative. We have to be careful though, because the force of gravity has a horizontal and vertical component. You might be asking, how do we tell the quantity of the vertical and the horizontal component of the gravity? This is where the theta comes in the bottom left corner of the triangle. We know that the vertical component of the gravity is equal in magnitude but opposite direction to the normal force. We are trying to recreate the big right angle triangle with a smaller right angle triangle, so we can reuse the angle theta within our smaller right triangle. In order to determine the location of theta in our smaller triangle, we need to refer back to the properties of similar triangles. Imagine the smaller triangle has been translated in a way in which the corresponding sides line up with each other. This means to line up the parallel line with the incline and the right angle with the other right angle. This will then line up theta to be in the location in the green. If this doesn't exactly click for you, it's okay. You can just memorize that the location of theta will always be in this spot on an inclined plane. Using the rules of trigonometry, we know that the opposite side to theta represents sine, and therefore we know that mg sine theta represents the horizontal component of gravity. And since we know the force of gravity is going against the motion, we know that this component, this horizontal component of gravity, is going to be negative within our system of equations. Finally, we can put our second equation together. We know that the force of tension is going upward along the incline, making it positive. And the horizontal component of gravity, as well as the force of friction, are acting against the motion along the incline, making it negative. You might be asking why we do not include the normal force within this equation, and the reason for that is that the normal force does not act in the direction of the motion. Since we have more than one unknown, we need a way to combine these equations in order to solve for the acceleration of the system. In order to do so, we need to recognize that the tension is equal for both masses since we are dealing with a frictionless pulley. With that said, there are two ways to solve a system of two equations, elimination and substitution. I am going to do substitution and isolate for force of tension in the second equation and sub that into the first. Once we've done that, it's just algebraic steps from there. It's important that when you sub ft back into the first equation, you keep brackets around that substitution. Therefore, you don't mix up which components are positive and which components are negative. We still have one more unknown, and that is the force of friction. Now, the formula for the force of friction is your mu, is your coefficient of your friction, times your normal force. On an incline, the vertical component of gravity is equal to the normal force, and therefore we're using cosine. So altogether, the force of friction is equal to 0.25 times your mass times the acceleration of gravity, cosine 30. This equates to 16.97 newtons. Now sub in all your values into the combined equation to isolate and find acceleration. We then calculate that our final answer for the acceleration of the system is 3.07 meters per second squared.
Thank you for watching Not That Complicated. Don't forget to like and subscribe.